Hi, welcome. So, you've been seeing LangChain everywhere, job listings, tutorials, people on LinkedIn talking about building AI agents, and you have zero idea what any of it actually means. What even is an LLM? What's RAG? What's an embedding? What's an agent? And underneath all of it, what is LangChain and why does it exist? This video answers all of that. From scratch after no shortcuts, no assumptions. I am going to explain every term before we get into the framework, so by the time we start building, nothing is confusing. We'll go through all terms, LangChain building blocks, and end with the exact project you should build to land a job in AI engineering. Let's go. Before we can talk about LangChain, we need to talk about what it's built on top of. What is an LLM? LLM stands for Large Language Model. I know, sounds intimidating. It's not. Here's what it actually is. An LLM is a computer program that was trained on an enormous amount of text. We're talking trillions of words. Books, websites, Wikipedia, GitHub code, academic papers, forum posts, news articles, basically a huge chunk of human writing. During training, the model's only job was to predict the next word in a sentence, over and over again, billions of times. If it got it wrong, it adjusted. If it got it right, it reinforced that pattern. After doing this across thousands of computers for weeks or months, the model becomes incredibly good at understanding and generating language. It learned grammar, facts, logic, how to write code, how to explain things just by predicting text. That's it. No magic, no consciousness. Just very advanced pattern recognition at a massive scale. Now, the real world versions you've heard of, GPT 4o, is made by OpenAI, the company behind ChatGPT. This is probably the most famous one. Claude is made by Anthropic. That's the AI you might already be using to research this stuff. Gemini is Google's version deeply integrated into Google Search and Workspace. Llama 3 is Meta's model, and this one's special because it's open source. Anyone can download and run it for free. LangChain works with ALL of these. You write your code once, and you can swap between any of them. We'll see exactly how in a few minutes. Okay, next term you'll hear constantly token. Here's the thing, AI doesn't read word by word the way you do. It reads in chunks called tokens. A token is roughly 3/4 of a word. So 1000 tokens is about 750 words, roughly 1.5 pages of text. Look at this example on screen. The sentence LangChain is amazing. Let's see how it gets tokenized. Lang is one token, chain is another, is one, Amaz is one, ing is the last one. 5 tokens total. Notice how it breaks at weird places, not at word boundaries but at subword chunks. That's because the tokenizer was built to be efficient, not readable. Why does this matter to you as a developer? Every model has a token limit, how much text it can process in one go. This is called the context window. GPT 4o handles around 128,000 tokens. Claude handles 2 lakh tokens, that's about 500 pages of text. Beyond that limit, the model literally cannot see the rest. It gets cut off. This is one of the reasons we need LangChain. When your documents are bigger than the context window, which they almost always are, you need a smart way to break them up and feed in only the relevant parts. We'll get to how that works. Next, what is an API? API is Application Programming Interface. This one confuses a lot of beginners, but the idea is incredibly simple. Think of a restaurant. You're the customer, that's your app, your Python code. The kitchen is the AI service, say OpenAI's servers where GPT-4 lives. The waiter is the API. You don't walk into the kitchen and cook your own food. You give your order to the waiter in a structured format, the waiter takes it to the kitchen and brings back the result. An API is that waiter. It's a structured way for your program to ask another service for something and get a result back. In practice, calling the OpenAI API looks like this. Step 1. Your Python code sends a question plus your API key, which is basically your password that proves you have an account. Step 2. OpenAI servers receive it. GPT-4o processes your message. Step 3. A response comes back in JSON format, a structured text format that Python can easily read and use. In code, it's literally just a few lines. You make a request, you get an answer. The API is the bridge between your code and the AI. LangChain wraps this bridge in a much cleaner, friendlier interface so you don't have to write all the low-level request handling yourself. Next, how does an LLM learn? Let me give you a slightly deeper model here because it'll help everything else make sense. Think of it like autocomplete on your phone, but trained on all of human writing for months on thousands of computers. Step 1. Collect data. We're talking trillions of words, the entire internet, every book you can imagine, every Wikipedia article, massive amounts of code from GitHub. This data is the raw material. Step 2. Predict the next word. The model takes a sentence, covers the last word, and tries to predict it. The sky is blank. It guesses. If it's wrong, it adjusts its internal numbers, millions of tiny adjustment knobs called parameters, to do better next time. Step 3. Repeat billions of times. This runs across thousands of specialized GPUs for weeks. The model keeps getting better and better at prediction across every domain, science, law, poetry, code, all of it. Step 4. Fine-tune and align. After initial training, human raters look at the model's responses and rate which ones are better. The model learns from this feedback to be more helpful, more accurate, and safer. This process is called RLHF, reinforcement learning from human feedback. The result? A model that can write code, answer questions, translate languages, summarize documents, because it's seen all of human knowledge expressed in text. Next, what is RAG? Okay, this one is probably the most important term in this whole video for practical AI engineering. RAG stands for Retrieval Augmented Generation. Terrible name. Great concept. Here's the analogy. Think about exams. A closed book exam is a standard LLM. It only knows what it memorized during training. If you ask it about something after its training cut off, or about your private company documents, it either makes something up or admits it doesn't know. An open book exam is RAG. Before answering, the AI is allowed to look up the relevant pages from your documents. Then it answers based on what it found. Here's exactly how it works in 4 steps. The user asks a question. The system searches a database of your documents for relevant content. The most relevant chunks get retrieved and handed to the AI as context. The AI reads that context and generates an accurate, grounded answer. Why does this matter so much? First, LLM have a knowledge cutoff. GPT-4 doesn't know what happened last week. RAG lets you feed in current information. Second, LLM don't know your data. Your company's internal documentation, your customer database, your product specs, none of that was in training. RAG lets you give the AI access to it at query time. Third, RAG fixes both problems without retraining the model from scratch, which would cost millions of dollars. This is the most used AI engineering pattern in production system. Miss LangChain makes building RAG pipelines almost trivially easy. We'll see exactly how. To make RAG work, we need one more concept, embeddings. Computers cannot understand words. They only understand numbers. An embedding takes a piece of text and converts it into a long list of numbers called a vector that mathematically captures the meaning of that text. Here is the model I want you to hold on to. Think of GPS coordinates, but instead of representing a location on a map, they represent meaning in language. Look at the examples on screen. The sentence, "How do I reset my password?" gets converted into thousands of numbers, something like 0.23, 0.87, 0.12, continuing for thousands of values. That full list of numbers is its vector. Now look at the second sentence, "Steps to change my password." Even though the words are completely different, the meaning is almost identical. So when it gets converted into numbers, those numbers land very close to the first one in that mathematical space. But look at the third sentence. "The weather in Tokyo today." Completely different topic, completely different meaning, and so the numbers land far away from the first two. This is how the AI finds the right documents for your question. It does not scan for matching keywords. Instead, it converts your question into a vector, then searches for all the stored document chunks whose vectors are closest in meaning. That is called semantic search, and it is far more powerful than simple keyword matching. Now, where do all these vectors get stored? In something called a vector database. This is a special kind of database built specifically for searching through millions of number lists at lightning speed and finding the closest matches. Three popular options you will hear about. First is ChromaDB free, runs on your own machine, zero setup required, perfect for learning and prototyping. Second is Pinecone, a cloud-based service great for production apps that need to scale. Third is PG Vector, which is an extension for Postgres, the same database that most backend companies already run, making it a natural fit for production systems. Next, before we get into LangChain, let's see what is a framework. Imagine you are building an AI application completely from scratch, with no help from anyone. Every single time you start a new project, you would have to write your own memory management system to track conversations. You would have to build your own PDF reader to extract text from files. You would have to code your own vector search logic to find relevant content. You would have to handle every API error manually, writing retry logic yourself every single time. That is an enormous amount of work before you have even started building the actual thing you wanted to build. You would be reinventing the wheel on every single project. Now compare that to using LangChain. Need memory? One line of code. Need a PDF loader? One line of code. Need vector search? One line of code. Error handling? Already built in. With a framework, all of that plumbing is handled for you. You stop worrying about the infrastructure and start focusing entirely on your application, the unique, valuable thing that only you are building. That is what a framework gives you. Code that has already been written, tested, and used by thousands of developers around the world so that you can move fast and build on a solid foundation instead of starting from zero. Here is a simple way to think about it. Imagine you are building a house. A framework is the scaffolding already set up around the site, the power tools ready to use, and the lumber already cut to size. You still design the house. You still build it. But you do not have to forge your own nails, mill your own wood, or invent your own tools before you can even begin. That is exactly what LangChain does for AI development. Alright, that is all the jargon covered. Now let us get into LangChain itself. Before we look at what LangChain gives you, let us first feel the pain of not having it. Imagine you have your language model set up. You call the API. You get responses back. Everything looks great for a simple one-off demo. But the moment you try to build something real, something that actual users will depend on, you hit four walls. The first wall is no memory. Every single message you send to the AI is a completely blank slate. The AI has no idea what you said one message ago, let alone 10 messages ago. If you wanted to remember anything, you have to manually collect every previous message and resend the entire conversation history yourself every single time. For a chatbot, this means your users have to repeat themselves over and over again. It makes for a frustrating and broken experience. The second wall is that the AI cannot read your files. Say you have a 200-page product manual and you want the AI to answer customer questions about it. The problem is you cannot paste 200 pages into a single prompt. It simply will not fit within the context window. You need a smarter way to extract only the relevant pages at the right moment and hand just those to the AI. The third wall is that the AI cannot take actions. Maybe you wanted to search the web for current pricing, or run a query against your database, or send a confirmation email to a customer. A raw language model cannot do any of that. It only generates text. You need an additional layer that connects the AI to real-world tools and services. The fourth wall is that it is hard to connect multiple steps together. Say you want to search a document, then summarize it, then translate it, then send to a customer. That is four separate AI calls. Wiring all of them together manually means writing a lot of repetitive, fragile code that breaks easily and is painful to maintain. LangChain solves every single one of these problems right out of the box. That is its entire purpose. So what exactly is LangChain? LangChain is an open-source Python framework first released in 2022 by a developer named Harrison Chase. It gives you a collection of pre-built tools for building production-ready applications powered by large language models. Here is the analogy that makes it click for most people. A large language model on its own is like a car engine. It is incredibly powerful. But an engine sitting alone in a garage does not get you anywhere. You cannot drive an engine LangChain is the whole car, the steering wheel, the gears, the fuel tank, the GPS navigation, the seat belts, all the surrounding pieces that take the raw power of the engine and turn it into something you can actually use to go somewhere. So, concretely, what does LangChain give you? Five categories of tools, which we are about to go through one by one. First, memory. So, the AI actually remembers your conversation from message to message. Second, document loaders. So, the AI can read your files, your PDFs, your websites, your data. Third, embeddings and vector search. So the AI can find the most relevant content based on meaning, not just keywords. Fourth, chains to connect multiple steps together into a clean, automated pipeline. And fifth, agents AI that can plan its own strategy and use tools autonomously to complete a goal. 7 building blocks in total. Let us go through each one right now. Remember all the large language models we talked about earlier? GPT, 4o, Claude, Gemini, and Llama? Each of these is made by a different company, has a different API, and works slightly differently under the hood. Normally, if you built your app around one of them and then wanted to switch, you would have to rewrite large chunks of your code. LangChain solves this by wrapping every single one of these models in the same unified interface. You interact with all of them in exactly the same way, using exactly the same code structure. What that means in practice is this. You write your application code once, and then swapping from one model to another is literally a single line change. For example, if you are using Chat Open AI for GPT 4o and you want to switch to Claude, you comment out that one line and replace it with Chat Anthropic. That is it. Every other line in your application stays exactly the same. This is enormously valuable in production. You can run the same task through multiple models and compare which one performs better. You can cut costs by routing simpler tasks to cheaper, faster models. And if one provider goes down or raises their prices, you can switch to another without touching any of your business logic. Building block number 2, prompt templates. If models are the brain, then prompt templates are the way you communicate with that brain in a structured, repeatable way. Here is the simplest way to think about it. You know the game Mad Libs, where you have a story with blank spaces and you fill in a word for each blank? A prompt template works exactly like that, but for AI instructions. Instead of writing out your full prompt from scratch every single time you want to ask the AI something, you define the structure of your message once, with placeholder slots for the parts that change. In LangChain, those placeholders are written inside curly braces. So, for example, you might define a template that says, answer this question clearly and concisely. Question. The word question inside the curly braces is the placeholder. Every time you run it, you simply pass in whatever the actual question is, and LangChain fills it into the right spot automatically. The structure of your message stays consistent every time. Only the content inside the placeholder changes. This matters far more than it might seem right now. In a real production AI application, you might have 20, 30, or even 50 different prompts, one for summarizing, one for translating, one for extracting data, one for generating a reply, and so on. Prompt templates let you keep all of those organized in one place, reuse them across your code base, track changes to them over time, and update them instantly without hunting through your code. Building block 3, memory. We talked about how large language models have zero memory by default. Every message is a blank slate, like talking to someone with amnesia. LangChain's memory components fix this automatically. You add a memory object to your chain, and from that point on, LangChain silently does two things. It saves every message to the memory store, and before every new message, it injects the conversation history into the prompt behind the scenes. The AI always has full context of the conversation. You write zero history management code, one line, conversation buffer memory. That is it. That is the entire setup. There are also smarter memory types. Conversation summary memory compresses old history to save tokens. Conversation entity memory specifically tracks names, places, and facts mentioned in the conversation. Building block 4, document loaders. LangChain can read almost any file format you can think of. PDF files, Word documents, spreadsheets, websites, Notion pages, Gmail, even YouTube video transcripts. For each source type, there is a pre-built loader that handles all the parsing complexity. Then comes the text splitter. Because documents are almost always too big for single prompt, the splitter breaks them into smaller overlapping chunks. The overlap, typically 50 tokens, means that even if a key sentence falls near the edge of a chunk, it still appears in the next chunk too. Nothing important gets lost between splits. Next, building block 5, embeddings and vector stores. Now we are getting to the heart of RAG. Here is the full flow. You have your document chunks from the text splitter. Each chunk gets converted into a vector, that list of numbers representing its meaning using an embedding model. All those vectors get stored in a vector database like ChromaDB. Now, when a user asks a question, the question itself also gets embedded into a vector. The vector database does a nearest neighbor search, instantly finding the stored vectors whose meanings are closest to the question. In vect, those matching chunks get returned and handed to the language model as context. The model answers based on real, relevant content, not guesswork. Think about the examples on screen. Reset my password and change my password are a close match, so they get returned as relevant. Tokyo weather today has no match, so it does not get returned. This is semantic search after no keywords required. It works across synonyms, paraphrases, and completely different phrasings of the same idea. ChromaDB is your starting point. Completely free, runs locally, zero setup. Once you are in production, PG Vector lets you use a regular PostgreSQL database for vector storage, which is exactly what companies use because they already have Postgres in their stack. Next, building block 6, chains. A chain is a sequence of steps that runs in a fixed order. One step's output becomes the next step's input. This is literally where the name LangChain comes from. Let's walk through a full RAG chain step by step. Step 1. The user asks a question. Step 2. That question gets embedded and used to search the vector store. Step 3. The most relevant document chunks come back. Step 4. Those chunks get injected into a prompt template along with the original question. Step 5. The language model reads the enriched prompt and generates an accurate, grounded answer. 5 steps, all happening automatically inside one chain. And in code, that entire pipeline is surprisingly short. You create a retrieval QA chain, pass it your model and your vector store as a retriever, and then call invoke with your question. That is the whole thing. One object, one call. The search, the context injection, the model call, all handled for you. That single invoke call does everything. That is the power of chaining. You compose pieces, and the framework handles all the wiring. Next, building block 7, agents. This is where things get really interesting. A chain follows a fixed sequence. You define the steps, they always run in that order. Predictable, reliable. An agent is smarter. The AI decides what to do. You give it a list of available tools and a goal, and it figures out the plan itself, which tools to use, in what order, and when to stop. Here is a concrete example. You ask the agent, what are the latest AI regulations and how might they affect our company's data policy? The agent reasons internally. First, it thinks I need current information about AI regulations, so I should use the web search tool. It searches and gets results. Then it thinks, now I have the regulatory context, but I need to compare it with our data policy. So let me check the company documents using the document search tool. It searches the vector store. Then it thinks, now I have both pieces and I can generate a comprehensive answer. The agent planned a multi-step strategy entirely on its own. You did not program those steps. You just gave it tools and a goal. Typical tools in a LangChain agent include web search to find current information, a calculator so the model does math accurately without hallucinating numbers, database queries to pull live data, and email sending to take real-world actions, not just generate text. You can even build your own custom tools. Any Python function can be wrapped into an agent tool in just a few lines. Agents are the foundation of autonomous AI systems. Miss this. is exactly what a company is building at scale. Agents that automatically engage leads, qualify them, and take follow-up actions across email, text message, and chat. Let's zoom out for a second. All 7 building blocks at a time. Number 1, model. The AI brain. GPT, Claude, Gemini, all through a unified interface. One line to swap between them. Number 2, prompt template. Fill in the blank messages, define once, reuse everywhere. Number 3, memory. Makes the AI remember the full conversation automatically. Number 4, document loader. Reads any file type into text chunks ready for processing. Number 5, embeddings and vector store. Makes your data searchable by meaning, not keywords. Number 6, chain. Connects steps into a pipeline. One call does everything end to end. Number 7, agent. AI that plans and uses tools autonomously to complete a goal. These 7 pieces are all you need to build production-grade AI applications. Everything in modern AI engineering is some combination of these concepts. Okay, knowledge is nothing without action. Let me tell you exactly what to build first. Build a document Q&A bot. The idea is simple. You upload a PDF and the bot can answer any question about it using AI. This is a real use case. Companies pay for this and it touches every single concept we just covered. Step 1, load a PDF. Pick any PDF. Your university syllabus, a company FAQ, a research paper. Use PyPDF loader from LangChain. 3 lines of code. Step 2, split and embed. Run it through the recursive character text splitter to break it into 500 token chunks with 50 token overlap. Then use OpenAI embeddings to convert every chunk into a vector. Step 3, store in ChromaDB. Feed all the vectors into ChromaDB. Feed all the vectors into ChromaDB. It runs locally, it is free, and no account is needed. Your document is now a searchable vector database. Step 4, build a fast API endpoint. Create a post endpoint at /ask. It receives a question, runs the full RAG chain, searches ChromaDB, builds a prompt, calls the language model, and returns the answer. This is a real API that other apps can call. Step 5, deploy with Docker. Write a Docker file that containerizes your entire app. Push it to AWS. Now it is live on the internet. That 5-step project uses Python, Fast API, LangChain, embeddings, ChromaDB, and Docker. That is the exact stack that companies run in production. You walk into an interview with that project on your GitHub, working, deployed, documented, and you are not a beginner anymore. You are someone who built a real AI system from scratch after. And that is a wrap. You went from not knowing what a large language model was to understanding all 7 LangChain building blocks, all the jargon that comes with them, and exactly what to build to prove it. Let me leave you with one thing. The gap between people who understand AI tools and people who can build with them is still wide open. Most people watch videos like this and do not do anything. If you go build that Q&A bot and put it on GitHub, even if it is imperfect, you are already ahead of most people applying for AI engineering roles right now. So go build it. If this video helped, drop a like. It genuinely helps more people find this content. Subscribe if you want more on fast API, PostgreSQL, AWS deployment, and building AI backends. That is all coming. See you in the next one.